You are sitting in a dark room. The air is still. You cannot see anything moving, and yet, as you read these words, something is passing through you. Through the walls, through the floor, through the bone of your skull and the soft tissue beneath, a stream of particles is moving at hundreds of kilometers per second. They cross the room in less than a millionth of a second. They do not strike your skin. They do not disturb a single atom in your body with any force you could ever feel. If you waited your entire life for one of these particles to strike a nucleus inside you, the odds are that it would never happen. And yet they are there, right now, billions of them every second, moving as though you were not there at all. About 85% of all the matter in the universe is this kind of matter. Everything you have ever seen, every star, every planet, every living thing, is a thin film of light resting on a vast invisible ocean. We can map this ocean. We can weigh it. We have no idea what it is. Hello, and welcome to Sidereal. This is a channel about space, about the things we have found and the things we have not, and about the scientists who spent their lives trying to tell the difference. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps the channel, and I would like to know where you are listening from. So if you feel like it, leave your location and the time in the comments. That is the only time I will ask. Tonight, there are 3 questions I want to carry with us. How did we become certain that most of the universe is invisible when we have never once held a piece of it in our hands? Why are we so sure it is not simply ordinary matter that happens to be too faint to see? And after nearly a century of looking, and 4 decades of building the most sensitive instruments in human history, why have we still not caught even one of these particles in the act? By the end, you will understand the long effort to see the unseen and why it matters that you are not made of the same stuff as the cosmos that produced you. The number that opens this whole story is the one I have already given you, 85%. That is not a rough guess. It is a measurement, extracted from the oldest light in the universe, and confirmed by the way galaxies move and cluster and bend the space around them. When astronomers tally the mass of everything that shines, everything made of protons and neutrons and electrons, they get about 15% of the total matter. The rest is something else. Something that does not interact with light. Something that is not on the periodic table. Something that has never been held in a laboratory or captured by a detector. And it is not just out there in the deep, between the galaxies. It is here, in the room with you. The local density of dark matter at the position of the Sun is about 1 proton mass for every 3 cubic centimeters. A volume the size of a small bedroom contains roughly 50 billionths of a kilogram of the stuff, which is to say, the mass of a single fine grain of sand. That grain of sand is not sitting still. It is a continuous storm of particles, each one moving at a speed that would carry it across the Atlantic Ocean in a heartbeat, and not one of them knows you are here. There is a number that makes the strangeness of this more concrete, and I will give it to you plainly, because it is the kind of number that settles in the mind and does not leave. Imagine a single dark matter particle with a mass around 100 times that of a proton. Then roughly 100,000 of those particles are passing through your body every second. 100,000 every second, threading the volume of your heart, your lungs, the soft dark space behind your eyes, and not one of them touches anything. The chance that any one of those particles will strike a single atomic nucleus inside you during your entire lifetime is so small that it is, for any practical purpose, 0. And if the particle is not heavy at all, if it is something far lighter, a particle called an axion, then the numbers stop being countable. In that case, the density is not 100,000 per second, but trillions upon trillions. The room is thick with them, thicker than the air you are breathing, and you still feel nothing. This is not a figure of speech. It is not a philosophical flourish. It is a physical fact, as solid as the surface beneath you. The dark matter is here, and it does not care about you. It passes through you the way light passes through glass, except that glass, at least, slows light down. Dark matter does not slow. It does not scatter. It does not even acknowledge the existence of ordinary matter, except through one thing, and that one thing is gravity. Gravity is the only messenger. Dark matter bends space, and we can see the bending. That is how we know it is real. We have maps of it. maps of its distribution across the whole observable universe, maps of the halos that wrap around individual galaxies, maps of how it behaves during titanic collisions between entire clusters of galaxies. We can point to regions of the sky and say, there is a cloud of dark matter there, and it weighs this much, and it is drifting in this direction, and we can trace the shape of it in the way it twists the light of the galaxies that lie behind it. We have all of this, and we still cannot tell you what it is. And what we do know begins with a single, difficult truth. The universe is not made of us. The matter that forms stars and planets and people is not the universe's preferred material. It is a trace contaminant, a minority ingredient. When you look up at the night sky, every point of light you see, every galaxy and nebula and planet is made from the same small handful of particles, the same protons and neutrons and electrons that make up your own hand. That is a deeply human thing to notice. And for most of history we assumed it was the complete inventory. It is not. The inventory of ordinary matter is almost an afterthought. The real architecture, the scaffolding that holds the universe together and gives it shape, is built from something else entirely. And to see why we are so confident of that, you have to leave the room. So leave it, move outward, out of the room, out of the atmosphere, past the planets, past the nearest stars, out beyond the edge of our own galaxy, into the spaces between galaxies, into the great web that stretches across the entire observable cosmos. Because it is only at that scale that the weight of what I have just told you becomes visible. And it is only at that scale that you can begin to understand how we became so certain that the invisible is real. The universe, seen on the largest scales, is not a random scattering of galaxies. It is a web. Filaments of galaxies, each of them millions of light years long, stretch across the void, meeting and crossing at dense knots where the great clusters sit. Between the filaments lie enormous empty regions, voids hundreds of millions of light years across, where almost nothing shines. This structure is not an accident, and it is not arbitrary. It is the imprint of conditions set in the first moments after the Big Bang, a faint pattern of slightly denser and slightly emptier regions in the primordial soup. And what grew that pattern into the web we see today was not ordinary matter. Ordinary matter could not have done it. Ordinary matter was bound up with light, and light fought back against every attempt to clump. The dark matter was free. To understand why, you have to rewind the universe to a time when it was only 380,000 years old. Before that moment, everything was a hot, dense plasma. Electrons and protons were not yet bound into atoms. They flew free, and the universe was opaque, a glowing fog through which no light could travel far. When the universe finally cooled enough for atoms to form, the fog lifted, and the light that had been trapped inside it was set loose. We see that light today, stretched and cooled by billions of years of expansion, has the cosmic microwave background, a faint glow arriving from every direction at once, carrying with it a photograph of the universe at that single instant. And that photograph shows us that the ordinary matter was smooth, almost perfectly smooth. The temperature varied from one patch of sky to another by only a few parts in 100,000. Over the next few 100 million years, gravity had to take those whisper-faint ripples and pull them into the first stars and the first galaxies. But there was a problem. There was not enough time. Ordinary matter could not clump fast enough on its own, because it was still feeling the outward pressure of radiation, a force that resisted every attempt at collapse. The dark matter felt no such pressure. It had already begun to gather long before the first atom existed. It had been gathering since the first fractions of a second. This is the idea that runs through every modern simulation of how the cosmos took shape. You take a box, a representative slice of the universe, and you fill it with dark matter particles. You give them the faint pattern of overdensities measured in that oldest light, and then you let gravity do its work and watch what happens over billions of simulated years. What grows out of it is the cosmic web. Filaments, voids, clusters, all of it, in the right sizes and the right proportions. Only then do you add the ordinary matter, just 5% of the total, and let it fall into the deep gravitational wells the dark matter has already carved. The gas pools at the bottom of those wells. It cools, it fragments, it ignites. The galaxies switch on at the intersections of the dark web, in exactly the places where we observe real galaxies today. Remove the dark matter from the same simulation, and you get nothing like the real sky. The structures come out too small, too late, and too feeble to match anything we see. It is worth dwelling on why the ordinary matter needs the dark matter so badly, because the reason is not obvious. Gravity, after all, pulls on ordinary matter just as it pulls on the dark. Why could the ordinary gas not have gathered itself into galaxies on its own, given enough time? The answer is that gas, unlike dark matter, fights back. As a cloud of gas tries to collapse, it heats up and builds pressure, and that pressure pushes outward against gravity and resists the collapse. For gas to fall all the way down and form stars, it has to shed that heat, radiating it away as light, and that takes time. In the early universe, working against the clock of cosmic expansion, the gas simply could not cool and collapse fast enough on its own. It needed help. It needed to fall into a gravitational well that was already deep, already waiting, dug in advance by something that felt no pressure and built no heat. The dark matter, indifferent to radiation, had been quietly collapsing since long before the first atom formed, carving exactly those deep wells. When the gas arrived, the hard part was already done. It tumbled into the waiting dark halos, cooled at the bottom, pooled, and ignited. Without the halo, the gas would still be drifting, thin and warm and formless, across an empty universe. The dark matter did not just add mass, it dug the trap that caught the light. There is a crucial detail hidden inside those simulations, and it tells us something specific about what the dark matter must be. The dark matter has to be slow. Physicists call it cold dark matter, and the word cold here means that the particles move slowly compared to the speed of light. This matters because of a process called free streaming. If the dark matter particles were light and fast, racing across the early universe at close to light speed, they would have streamed straight out of the small clumps before those clumps could collapse, smearing out all the small-scale structure. In that kind of universe, the largest structures would form first, enormous sheets and pancakes of matter, which would only later fragment into galaxies. That is called top-down formation, and it was a serious proposal once, championed by the Soviet physicist Yakov Zeldovich and his school in Moscow. But it does not match what we see. What we see is the opposite. Small galaxies formed first in the early universe, and then merged and built themselves up into larger ones over billions of years. That is bottom-up formation, and it can only happen if the dark matter is cold and slow, able to clump on small scales from the very beginning. The structure of the universe, the shape of the web itself, is a fossil record of the speed of the dark matter particle, and it tells us that whatever the particle is, it was born moving slowly. This single requirement, that the dark matter be cold, has a sharp and inconvenient consequence. There is one particle we already know exists that could, in principle, be dark matter: the neutrino. Neutrinos are real. We make them in nuclear reactors. They pour out of the sun in unimaginable numbers, and they barely interact with anything, which is exactly the behavior you want from dark matter. For a while, in the 1970s and early 80s, many physicists hoped the neutrino would solve the whole problem. It was the obvious candidate, the one piece of dark matter we could be sure was out there. But the neutrino is light, and it is fast. It is hot dark matter. A universe whose dark matter was made of neutrinos would form structure top-down, in the wrong order, and it would not look like our universe at all. So the one dark matter particle we know to exist is ruled out by the shape of the cosmic web. The thing that built the structure has to be something we have never seen. The work that established all of this was done by a small group of theorists in the early 1980s, sometimes remembered as the Gang of Four: Mark Davis, George Efstathiou, Carlos Frenk, and Simon White ran some of the first detailed simulations of cold dark matter and showed that it reproduced the observed clustering of galaxies in a way that hot dark matter never could. 2 decades later, a German astrophysicist named Volker Springel, working at the Max Planck Institute for Astrophysics, led the construction of the Millennium simulation, completed in the year 2005. It followed more than 10 billion particles through the entire history of a representative chunk of the universe, and the cosmic web that emerged was so faithful to the real distribution of galaxies that it became one of the foundations of modern cosmology. When you see those deep, branching, luminous images of simulated structure, the ones that look like the neurons of an enormous brain, you are looking at the work of people who fed gravity nothing but cold, dark, invisible matter and watched it grow a universe. And we are no longer limited to simulating that web or to inferring it from the galaxies that happen to light up its densest knots. We can now photograph the dark matter almost directly by mapping the way its gravity bends the light of millions of distant galaxies across the sky. Every faint galaxy in the deep universe has had its image very slightly distorted by all the dark matter lying along the path between it and us, sheared by a tiny amount, far too small to notice in any single galaxy, but measurable as a faint statistical pattern shared across millions of them. Enormous surveys, with names like the Dark Energy Survey, have used this gentle, universe-wide shearing to construct maps of where the dark matter actually lies across huge patches of the sky. The cosmic web traced not by the light it emits, which is none, but by the light it bends. A new generation of instruments is now extending those maps further still, including a European spacecraft named Euclid, launched in 2023, whose mission is to chart the distribution of dark matter across much of the observable universe. The web that the simulations grew from nothing but cold dark matter is turning out, patch by careful patch, to be really there, written into the sky in the faint distortion of distant light. Sometimes the bending is not faint at all. When a massive cluster of galaxies sits almost exactly in front of a distant galaxy, the cluster's gravity can smear that background galaxy into long, luminous, curving arcs, or even bend its light into a complete ring of light encircling the cluster, a shape known as an Einstein ring, after the man whose theory predicted it. These dramatic arcs are not subtle statistics. They are visible directly in the images, glowing streaks wrapped around the heart of a cluster, and the amount of bending reveals the total mass of the cluster doing the bending, including all the mass that gives off no light. Time and again, when astronomers weigh a cluster this way, by the arcs it produces, they find far more mass than the visible galaxies and even the hot gas can supply. The light of the distant universe, on its long journey to us, is quietly mapping the dark matter it passes, drawing for us the outline of the very thing we cannot see. It was the technique Fritz Zwicky imagined in 1937, when no instrument on Earth could attempt it, and it has become one of the most reliable scales we have for weighing the invisible. The numbers that come out of this work are not vague. The total content of the universe divides into three parts. Ordinary matter, the stuff of the periodic table, the stuff of stars and planets and people, makes up 4.9%. Dark matter makes up 26.8%, and the remainder, 68.3%, is dark energy, which is a separate mystery and a story for another night. But set the dark energy aside and look only at the matter. There, dark matter outweighs ordinary matter by more than 5 to 1. For every kilogram of protons and neutrons in existence, there are more than 5 kilograms of something invisible, something that fits into no known category of particle. And there is a quiet mystery folded inside that ratio that deserves a mention, because it is the kind of thing that does not have an answer yet. Why 5 to 1? The dark matter and the ordinary matter were made by completely different processes in the early universe, governed by different physics, with no obvious reason to come out in any particular proportion to each other. They could have differed by a factor of 1,000,000 or 1,000,000,000 in either direction. Instead, they came out within a single factor of 5, close enough to be comparable, far enough apart that the dark clearly dominates. Nobody knows why the two amounts should be so near in scale. It may be a pure coincidence. It may be a clue to some deeper connection between the dark sector and our own, some shared origin in the first instance of the universe that we have not yet uncovered. It is one of those numbers that sits in plain sight, fully measured and completely unexplained, waiting for a theory that can say why it is what it is. And this ratio is not a knob we are free to turn. It is measured independently from several completely different lines of evidence. The oldest light gives one number. The way galaxies cluster across the sky gives a matching number. The amounts of the lightest chemical elements, forged in the first 3 minutes after the Big Bang, give yet another, and all of them agree. The matter of the universe is overwhelmingly dark. Our own galaxy, the Milky Way, is one small knot in this enormous web. The visible disk, the bright spiral of stars and gas and dust that fills every photograph, is about 100,000 light-years across. But the dark halo that surrounds it reaches out at least 650,000 light-years, and perhaps a great deal further. Its total mass is roughly 1 trillion times the mass of the Sun, and most of that mass is not in the disk at all. Most of it lies in a vast, roughly spherical cloud of dark matter that swallows the bright galaxy whole, a cloud we cannot see but whose pull we can read in the motion of every star. The person who first put a name to this invisible component, the person who first used the term that would survive into our own century, was not looking at a single galaxy. He was looking at a whole cluster of them. His name was Fritz Zwicky, and he is one of the strangest and most exasperating figures in the history of science. Before we follow him, though, hold on to one thing about the architecture I have just described. It is not merely that the dark matter exists, or that it is heavy, or that it is everywhere. It is that your existence depends on it having gone first. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of it was forged inside stars. And those stars ignited inside galaxies, and those galaxies formed because the dark matter had already built the wells for the gas to fall into. Take the dark matter away, and you do not simply lose an invisible substance. You lose the stars. You lose the planets. You lose the very possibility of anything complex ever assembling itself. The invisible made the visible possible. That is the thought to carry as we go back to the difficult man who started all of this. He was not easy to like. Fritz Zwicky was born in 1898 in the Bulgarian town of Varna, the son of Swiss parents, and he remained a Swiss citizen his entire life, even after he settled in California. He spent most of his career at the California Institute of Technology, and he had a rare and consistent gift for making enemies. He referred to colleagues he disliked as spherical bastards. On the grounds, he explained, that they were bastards no matter which way you looked at them. He called other astronomers scatterbrains. He was brilliant. He knew he was brilliant, and he had no patience whatsoever for those who could not keep up, which in practice meant nearly everyone. That temperament would cost him dearly. When he made one of the most important discoveries in the history of cosmology, the community he had spent years insulting largely shrugged and looked away. It would take 40 years for the field to circle back and admit that he had been right. The year was 1933. Zwicky was studying the Coma cluster, a rich swarm of galaxies in the constellation Coma Berenices, lying about 320 million light-years away. He had access to the velocity measurements of a remarkable man named Milton Humason, a former mule driver and tobacco-chewing high school dropout who had talked his way into a job at Mount Wilson Observatory and become one of the finest observational astronomers of his generation. Humason could read the velocity of a galaxy from the shift of the lines in its spectrum, and he had been patiently building a catalogue of those velocities that no one in the world could match. Zwicky took the velocities Humason had gathered and applied a piece of classical physics called the virial theorem, which connects the average speed of the objects in a gravitationally bound system to the total mass holding that system together. The reasoning is simple enough to hold in your head. In a cluster, every galaxy is moving under the combined gravitational pull of all the others. Measure how fast they are moving, and you can work out how much total mass must be present to keep them from flying apart. Too little mass, and the cluster would have scattered into the dark long ago. Zwicky did the arithmetic, and what came back should not have been possible. The galaxies in the Coma cluster were moving far too fast. To hold them together, the cluster needed a total mass roughly 400 times greater than the mass he could account for in the visible stars. 400 times. Even when he made generous allowance for gas and dust and faint, hard-to-see objects, the numbers did not close. They did not come anywhere near closing. Zwicky published the result in a Swiss journal, in German, and in that paper he reached for a phrase that would outlive him by a century. He called the missing component dunkel materia, dark matter. He was not, strictly, the first to suspect that the universe held unseen mass. A decade earlier, the Dutch astronomer Jacobus Kapteyn had studied the motions of stars in our own galaxy and concluded that there must be some dark material in the galactic plane, though he assumed it was simply faint stars and cold gas too dim to register on his plates. In 1932, another Dutch astronomer, Jan Oort, had reached a similar conclusion from the way stars bob up and down through the galactic disk. He too believed the missing mass was ordinary, just unlit. Oort measured how quickly stars oscillated through the plane of the Milky Way as they orbited, a motion governed by the pull of all the matter in the disk, and he found a hint that there might be more mass near the galactic plane than the visible stars could account for. The amount he inferred came to be called the Oort limit, and for decades it sat in the literature as a modest puzzle, the kind of small discrepancy that might be explained away by faint stars and dim clouds. Neither Captain nor Oort imagined a new substance. They were measuring the gravity of our own galactic neighbourhood and finding it slightly heavier than the starlight suggested, and they reasonably assumed the extra weight was simply matter too faint to register. The leap that Zwicky made, and that they did not, was in scale and in nerve. Zwicky's number was of a different order entirely. A factor of 400 could not be explained away by a handful of dead stars. It was not a small correction at the margins. It was a catastrophe for the accepted picture of the universe. As it happened, Zwicky's number was wrong, though the error was not his fault. The Hubble constant, the figure that relates a galaxy's redshift to its distance, was very poorly known in 1933. The value available to him was far too large, which threw off his distance to the Coma cluster, which in turn inflated the apparent mass discrepancy. When later astronomers redid the calculation with a more accurate Hubble constant, the gap shrank. Modern measurements give the Coma cluster a total mass of about 1,000 trillion times the mass of the Sun, of which the luminous matter contributes around 15%, so the missing factor is closer to 7 than to 400, but the essential discovery was untouched, and it was still enormous. The overwhelming majority of the mass in the Coma cluster was not shining. Zwicky had been right about the thing that mattered, even while he was wrong about the size of it. There is a wrinkle here that took another 40 years and a new kind of telescope to uncover, and it makes the results stranger, not weaker. When Zwicky weighed the Coma cluster, he compared the total mass to the light of its stars. But the stars, it turns out, are not where most of the ordinary matter in a cluster lives. When astronomers learned to observe the sky in X-rays, lifting their instruments above the atmosphere that blocks that light, they discovered that the space between the galaxies in a cluster is not empty at all. It is filled with an enormous, thin, ferociously hot gas, heated to tens of millions of degrees, glowing in X-rays across the whole cluster. And that intergalactic gas holds far more ordinary matter than all the stars in all the galaxies combined, several times more. So the accounting changed. The visible stars were only a fraction of the ordinary matter. The hot gas was the larger share. And yet, even after adding in all of that gas, all the ordinary matter that the X-ray glow revealed, the cluster was still far too heavy. The mass needed to hold it together still dwarfed everything that could be seen by any means at all. The hot gas did not solve the missing mass. It only sharpened the question by accounting for most of the ordinary matter and showing, beyond argument, that the rest was something else. What happened next is a lesson in how science actually works, which is to say, through human beings, with all their grudges intact. Zwicky's paper was barely cited. It set off no rush of follow-up studies. No one raced to their telescopes to confirm or refute it. The community simply set it aside. Part of this was the sheer extremity of the claim, which seemed more likely to be a mistake than a revelation. But part of it, an undeniable part, was Zwicky himself. He had burned so many bridges and insulted so many colleagues that when he announced something genuinely remarkable, people were inclined to assume he was exaggerating again. He had a long record of grand pronouncements, and some of them had been wrong. So the missing mass became a curiosity filed away in a drawer, while the field moved on to questions raised by people who were easier to work with. And here is the part of Zwicky's story that should make you sit up, because it reveals just how far ahead of his time he really was. The dark matter paper was not even his most prophetic work of that decade. In 1934, only a year later, working with the astronomer Walter Baade, Zwicky coined the word supernova and proposed that these brilliant stellar explosions mark the moment an ordinary star collapsed into a new kind of object. A star made almost entirely of neutrons, packed to unimaginable density. The neutron itself had been discovered only 2 years earlier. Neutron stars would not be confirmed by observation until 1967, more than 3 decades after Zwicky described them. In the same period, he and Bade suggested that supernovae were the source of cosmic rays, the high-energy particles that rain down on the Earth from deep space. And then, in 1937, Zwicky proposed something that completes the story in a way almost too neat to believe. He argued that the gravity of a galaxy could bend the light of objects behind it, turning the galaxy into a kind of lens, and that by measuring how the light was bent, astronomers could weigh the galaxy directly, including whatever invisible mass it might contain. Gravitational lensing, the exact technique that would one day be used to map dark matter across the sky, proposed by the same difficult man who first named the dark matter, decades before anyone had the instruments to attempt it. He saw the problem and he saw the solution, and he had to wait the rest of his life for the world to catch up. Zwicky compiled a 6-volume catalogue of galaxies and clusters, threw paper across lecture halls when he was bored, climbed mountains, and gave away much of his money to the orphans of the war. He was generous and impossible in roughly equal measure, and when he died in 1974, the discovery that would secure his place in history was only just beginning to be taken seriously. For the 40 years between Zwicky's measurement and that revival, the missing mass problem did not quite vanish, but it did not advance either. A handful of papers appeared and were forgotten. In 1959, 2 astronomers, Franz Kahn and Lodewijk Volcher, studied the slow approach of the Andromeda Galaxy toward the Milky Way, the 2 of them destined to merge billions of years from now, and calculated that the local group of galaxies had to weigh far more than its visible matter to move the way it did. Again, something was missing, but the evidence stayed scattered, and the community was not ready to face what it implied. It is difficult, from where we stand now, to feel how strange the idea of unseen matter once seemed. The belief that the universe was made of the same stuff as the sun and the earth and the stars was not a casual assumption. It was a deep intuition, almost an article of faith. To say that most of the matter in existence was something else, something invisible, something that could never be touched or seen, felt less like a discovery than like a confession of failure, a placeholder for ignorance dressed up as a physical thing. That began to change in the 1970s, and it changed because of a woman named Vera Rubin. Rubin was born in 1928 in Philadelphia, and she fell for astronomy as a child, watching the stars wheel past her bedroom window and building her first telescope from a cardboard tube and a lens her father helped her grind. She studied astronomy at Vassar College, and when she applied to graduate school at Princeton, she was turned away because Princeton did not admit women to its astronomy program. That policy would stand until 1975. So she went to Cornell instead, and then to Georgetown for her doctorate, where she studied the large-scale motions of galaxies and asked whether they were scattered randomly through space or gathered into clusters. Her thesis found evidence for clustering, and the field met it with skepticism. As it would meet much of her early work, she would find something genuinely interesting, and the response would be a polite suggestion that she had probably made a mistake. By the time she chose her next major project, she deliberately picked a quiet, uncontroversial problem, something no one would fight her over. She chose the rotation of galaxies. It would turn out to be one of the most consequential choices in 20th century astronomy. By the late 1960s, Rubin was working at the Carnegie Institution of Washington in partnership with an instrument builder named Kent Ford. Ford had developed an image tube spectrograph, a device that amplified faint light and recorded a spectrum far more efficiently than the photographic plates astronomers had relied on for decades. With it, the 2 of them could measure the velocities of stars and glowing gas in distant galaxies to a precision that had simply not been possible before. They turned the instrument on the rotation of spiral galaxies, and the question they were asking was a clean one. In a spiral galaxy, the stars and gas orbit the center, and the speed of any given orbit should depend on how much mass lies inside it. The Sun orbits the center of the Milky Way at a speed set by all the stars and gas closer in than we are. As you move outward from a galaxy's center, you eventually pass nearly all of its visible mass, and beyond that point the orbital speeds ought to fall away. This is how the solar system behaves. The inner planets race, the outer planets crawl. Mercury laps the Sun in 88 days. Neptune takes 165 years. That falling off of speed with distance is named for Johannes Kepler, and every astronomer alive expected to see it written into the spin of every galaxy. Rubin and Ford pointed the spectrograph at Andromeda, the great spiral that is our nearest large galactic neighbour, and measured the velocities of stars and gas clouds at a range of distances from its centre. What they found did not make sense. The rotation curve did not fall. It climbed, and then it flattened, and then it stayed flat, all the way out to the visible edge of the disk. The stars at the far rim of Andromeda were moving just as fast as the stars near its heart. Under the gravity of the visible mass alone, that was impossible. If the galaxy held only the stars and gas that could be seen, those outer stars should have been flung off into the dark long ago. The fact that they were still there, still circling, still bound, meant that there was a great deal more mass than anyone could see, and that the extra mass reached far beyond the glowing edge of the galaxy. She did not rush to announce a discovery. She was cautious by temperament, and twice cautious after years of having her results doubted. She checked for instrumental errors. She wondered whether Andromeda was simply a peculiar galaxy, or whether some systematic effect had crept into the measurements. So she and Ford observed more galaxies, and then more, working their way through one spiral after another. Every single one told the same story. Every one showed the same stubbornly flat rotation curve. Every one demanded a massive, invisible halo extending far past the stars. By the late 1970s, Rubin had published a definitive study of 10 bright spiral galaxies, and the conclusion could no longer be avoided. These galaxies were embedded in dark halos holding roughly 10 times the mass of everything that shone. Her own way of stating it was characteristically plain. The ratio of dark to luminous matter in a spiral galaxy, she said, was about 10 to 1, and that, she added, was a great deal of dark matter. There is a photograph of Vera Rubin from those years, standing beside a telescope, bent over a photographic plate, her face set in an expression of quiet concentration. She was not a performer. She held no dramatic press conferences and made no sweeping declarations. She gathered her data and let the numbers carry the argument, and the numbers carried it loudly. By the early 1980s, the flat rotation curves had been confirmed by independent groups around the world. There was a particularly powerful confirmation from radio astronomy, which could see something the optical telescopes could not. Spiral galaxies are surrounded by vast, thin disks of cold hydrogen gas that reach far beyond the visible edge of the stars, and that gas glows faintly at a radio wavelength of about 21 centimeters. By tracing the motion of this hydrogen, radio astronomers could measure the rotation of a galaxy out to distances where there were almost no stars left to observe at all, far past the bright optical disk and deep into the dark halo. A Dutch astronomer named Albert Bosma made this his doctoral work in the late 1970s, mapping the hydrogen rotation of a whole sample of spiral galaxies, and the curve stayed flat far beyond the starlight, exactly where the dark matter was supposed to dominate. This mattered enormously, because it pushed the evidence out into the region where the visible matter had almost entirely run out, and yet the gravity had not. The optical curves told you the halo was there. The radio curves told you how far it reached, and the answer was much further than anyone could see. The missing mass was no longer a curiosity in a drawer. It was a crisis at the center of astronomy, and it demanded an answer. Rubin herself became, late in life, the most prominent advocate in her field for the inclusion of women in science, mentoring a generation who came after her. She received the Gold Medal of the Royal Astronomical Society, only the second woman ever to do so, the first having been Caroline Herschel back in 1828. Many believed she had earned a Nobel Prize. She never received one. She died in 2016. At the age of 88, having lived to see the question she opened become one of the defining puzzles of physics, and having never once claimed to know the answer, Rubin was not, strictly speaking, the very first person to glimpse the hint. As far back as 1939, a young astronomer named Horace Babcock had measured the rotation of Andromeda and found that its outer regions seemed to be turning surprisingly fast, though his data were rough and he reached for other explanations rather than unseen mass. In the early 1970s, a radio astronomer named Morton Roberts pushed the measurement much further out than visible starlight could reach, tracing Andromeda's spin by the radio glow of its cold hydrogen gas, far beyond the edge of the bright disk, and he too found the curve stayed stubbornly, impossibly flat out into the darkness. What set Rubin's work apart was not that she alone saw it was that she saw it cleanly, and repeatedly, across galaxy after galaxy, with a precision that left no room to look away, and at a moment when the rest of the evidence had finally ripened enough for the field to believe her. Discovery in science is rarely a single thunderclap. It is more often a thing glimpsed faintly by several people across decades, until one of them sees it clearly enough, and often enough, that it can no longer be denied. At almost the same moment that Rubin was gathering her curves at the telescope, two theorists at Princeton arrived at the same conclusion from a completely different direction. Jeremiah Oestreicher and James Peebles had been worrying about the stability of spiral disks. A spiral galaxy is a thin, spinning sheet of stars, and a sheet like that is dynamically fragile. Left to itself, without a large spherical halo of mass to steady it, it should buckle and warp and tear itself into a bar within a fraction of the age of the universe. The only way to keep a spiral spinning serenely for billions of years was to wrap it inside a massive, invisible halo. Oestreicher and Peebles published their argument in 1973, and the convergence was striking. Theory, worrying about stability, and observation, watching stars at the rim, had walked toward each other from opposite ends of the problem and met in the middle. The dark halos were real. The question was no longer whether they existed. The question was what they were made of. The mass involved is worth pausing on, because it changes how you see every photograph of a galaxy you will ever look at again. The dark halo required to explain the Milky Way's rotation is about 1 trillion times the mass of the Sun. The visible stars and gas amount to perhaps 100 billion solar masses. The dark outweighs the bright by a factor of roughly 10. So when you look at one of those luminous spirals, the swirl of stars and the dark lanes of dust filling the frame, you are not looking at the galaxy. You are looking at the bright center of something vastly larger, a thin, glowing wafer suspended at the heart of an immense dark sphere. The dark matter around the Milky Way reaches out at least 200 kiloparsecs, which is 650,000 light-years, and the visible disk is barely a sixth of that across. You could travel outward from the galactic center, through the crowded stars, past the last spiral arm, past the thinning gas, on into the blackness where the starlight gives out entirely, and you would still be deep inside the dark halo for hundreds of thousands of light-years more. There is no edge that anyone has found. The halo simply fades, its density falling away with distance, and where it truly ends, no one can say. And we are not floating still inside that halo, we are ploughing through it. The Sun, carrying the Earth and everything on it, orbits the center of the galaxy at roughly 230 kilometers per second, and the dark halo, being a great pressureless cloud rather than a spinning disk, does not turn along with us in the same orderly way. So from where we sit, there is a wind, a steady stream of dark matter particles blowing against the solar system as we move, arriving from the direction of the constellation Cygnus, the Swan, the part of the sky toward which the Sun is traveling. It is this wind that the underground detectors are straining to feel, and it is this wind whose strength rises and falls across the year as the Earth's own orbit adds to, and then subtracts from, the Sun's motion through the galaxy. The particles passing through your body as you lie there are not arriving evenly from every direction. There is a current to them, a prevailing direction, a faint cosmic weather you will never sense, but which a sensitive enough instrument could, in principle, learn to read the way a wind sock reads the air. For most of the history of this subject, astronomers pictured that halo as smooth and featureless, a calm spherical fog wrapped around the galaxy. In just the last few years, that comfortable picture has been complicated and made far more interesting by a single spacecraft. The European satellite named Gaia has spent more than a decade measuring the precise positions and motions of nearly 2 billion stars, building the most detailed map of the Milky Way that has ever existed. And hidden inside the motions of those stars are the ghosts of ancient collisions. Gaia revealed that the inner halo of our galaxy is dominated by the shattered debris of another galaxy, a substantial one that the Milky Way swallowed whole around 10 billion years ago. The wreckage still moves together, even now, as a recognizable population of stars on similar orbits, the fossil of what was once a separate world. The dark matter of that devoured galaxy is presumably still here too, stirred into our own halo, which means the local dark matter wind may not be a single smooth stream at all, but a thing of currents and eddies, of streams and shells, the layered remains of everything the Milky Way has ever eaten. The wind blowing through this room may carry the dark matter of more than one galaxy, mixed together over the slow course of billions of years. Now, the causal chain I asked you to carry comes back with its full weight behind it. I said that the carbon in your cells and the oxygen in your blood and the calcium in your bones were all forged inside stars, and that those stars burned inside galaxies, and that the galaxies formed because the dark matter went first. You can now see the mechanism plainly. The stars that built your atoms were not scattered at random through the void. They formed inside the Milky Way, in dense knots of gas that collapsed within the dark halo. And the Milky Way itself exists only because a region of dark matter, slightly denser than its surroundings, began drawing ordinary matter inward more than 13 billion years ago. That ordinary matter cooled and fragmented and lit up as the first generation of stars. Those stars lived and died and seeded the gas around them with heavier elements. The cycle repeated through generation after generation of stars, each one enriching the gas with a little more carbon, a little more oxygen, a little more iron, until, about 4.5 billion years ago, one enriched cloud collapsed to make the sun and its planets. Every atom in your body heavier than hydrogen and helium was made in a star, and that star existed because dark matter held the galaxy together long enough for it to form. You are downstream of the invisible. You are a consequence of something you will never be able to touch. That is a causal chain, not a poem. Remove the dark matter and the faint ripples in the early universe are too weak to grow. The gas never falls into wells deep enough to form stars. The first galaxies never condense. The cosmic web never weaves itself. The universe stays a thin, cooling broth of hydrogen and helium, expanding forever in the dark, never lighting up, never building anything more complicated than an atom. The dark matter went first. It built the scaffolding. It dug the wells that caught the gas. It steadied the disks that became the galaxies. And inside one of those galaxies, around one unremarkable star, a planet cooled to just the temperature where chemistry could begin its long, improbable climb towards something that could eventually lie in the dark and wonder about all of this. The thing passing through your body right now, the thing you cannot feel, is the reason you have a body at all. Consider one more figure before we move on, because the figures are what keep this honest. When astronomers weigh a galaxy by its rotation and compare that to the mass of everything they can see, they get a ratio. For the Milky Way, it is about 10:1, but for the smallest galaxies, the dwarf spheroidals that drift around the Milky Way like moths around a lamp, the ratio can climb to 100:1, or even 1,000:1. These tiny galaxies are almost pure dark matter. They hold so few stars that some of them were not discovered until the 1990s, and a few not until this century. And yet the handful of stars they do contain moves so quickly that the galaxies must be drowning in unseen mass. The dark matter does not lay itself out in proportion to the light. It follows its own logic, keeps its own distribution, holds its own relationship to the visible universe, and we are only now beginning to map the shape of it. All of which brings us, at last, to the question that Rubin's curves made impossible to dodge. The dark matter is there. It outweighs the visible by 10:1 in our galaxy, and by far more in others. It built the structure of the cosmos. But what is it? It cannot be ordinary matter, because ordinary matter interacts with light, and in these quantities we would see it. It cannot be stars, because stars shine. It cannot be gas, because gas glows and absorbs at particular wavelengths and gives itself away. It cannot be dust, because dust blocks the light behind it and warms and shines in the infrared. Every form of ordinary matter we know leaves a fingerprint somewhere across the spectrum of light. The dark matter leaves nothing. The next move in the story, then, is the slow, careful elimination of every ordinary explanation, the demonstration from several independent directions at once, that the dark matter is not merely dark in the sense of being faint or far away, but dark in a far deeper sense, that it is not made of protons and neutrons at all, that it is something genuinely new. The evidence from rotation curves and cluster dynamics had made one thing clear by the 1980s. Most of the matter in the universe was not shining, but there was still an escape route, and for a long time a great many sensible astronomers walked down it. The dark matter, they argued, could be perfectly ordinary, just hidden in forms that were hard to see, Burned-out stars, cold, dark clouds of gas, faint brown dwarfs, those failed stars too small to ever ignite proper fusion. Black holes left behind when massive stars died, planets adrift between the stars, bound to no sun at all. The universe could be littered with such things, dark to our telescopes, and together they might account for the missing mass without requiring a single new particle. The appeal of this idea was obvious. It asked no one to believe in exotic physics. It did not require rewriting the standard model of particle physics, the hard-won catalogue of every known fundamental particle. It simply said that the cosmos held a lot of ordinary stuff that happened to be hard to spot, made of the same protons and neutrons and electrons as everything else, stuff that had slipped through the gaps in our surveys. Astronomers even gave these hypothetical objects a name. With the dry humour the field reserves for its deepest puzzles, they called them MACOs, for massive compact halo objects. The name was a deliberate joke at the expense of the rival candidate, the WIMP, the weakly interacting massive particle, which was the leading exotic possibility. The question underneath the wordplay was deadly serious. Was the dark halo of our galaxy built from MACOs or from WIMPs, from ordinary dark things, or from something fundamentally new? There were two ways to settle it. One was to count the total amount of ordinary matter in the universe from first principles, using the physics of the Big Bang itself. The other was to go out and hunt for MACOs directly. Both were attempted, and both pointed, in the end, to the same answer. The first approach rests on one of the most beautiful pieces of reasoning in all of cosmology, the study of how the lightest elements were made. In the first 3 minutes after the Big Bang, the entire universe was a thermonuclear furnace, hot enough and dense enough for protons and neutrons to fuse into the nuclei of the lightest elements. How much of each element came out of that furnace depended, with exquisite sensitivity, on the density of ordinary matter at the time. A denser universe would have forged more helium, a thinner one, less. The same logic governs the trace amounts of deuterium, a heavy form of hydrogen, and lithium. Deuterium is especially telling, and physicists sometimes call it the baryometer, the measure of ordinary matter, because of one crucial fact. Deuterium is fragile. Stars destroy it, and no natural process makes it in any quantity after those first few minutes. So every atom of deuterium in the universe today is a survivor from the birth of everything, and its abundance is a direct readout of how much ordinary matter the early universe contained. Measure the deuterium in ancient pristine clouds of gas, lit from behind by distant quasars, and you can weigh all the ordinary matter in creation. The answer that comes back is small. The density of ordinary matter needed to produce the deuterium and helium we actually observe is only about 4% of the total energy of the universe. But the total matter density, measured from the way galaxies and clusters move, is closer to 30%. Ordinary matter is only a small slice of the whole. If the calculations of those first 3 minutes are correct, and they have been tested against the data again and again, then most of the dark matter simply cannot be protons and neutrons. It has to be something else. The key figure in establishing this was an American physicist named David Schramm, who spent most of his career at the University of Chicago. Schramm was a mountain of a man, a former championship wrestler who brought a wrestler's combative energy into cosmology and was known, inevitably, as Big Bang Schramm. He was among the first to argue, loudly and relentlessly, that the abundances of the light elements ruled out a universe made wholly of ordinary matter. Through the 1970s and 80s, he and his collaborators sharpened the calculation and tightened the limits, until by the early 90s the case was overwhelming. Ordinary matter could account for no more than about 1/6 of all the matter. The rest had to be non-baryonic, which is simply the technical way of saying not made of the kind of particles that build atoms. Schramm was also a passionate pilot, and in 1997 he died when the small plane he was flying went down. He did not live to see the final confirmation of the picture he had fought for, which arrived from the oldest light in the universe only a few years later. The story of those first 3 minutes is not entirely tidy, and the honest version of it includes a loose thread that has never been pulled clean. The predicted amounts of deuterium and helium match the observations beautifully, which is the triumph that lets us weigh the ordinary matter of the cosmos. But the predicted amount of lithium does not match. When astronomers measure the lithium in the oldest, most pristine stars they can find, the ones that should preserve the chemistry of the early universe, most faithfully, They consistently find about 3 times less of it than the theory of the first 3 minutes insists there should be. This is the cosmological lithium problem, and after decades of effort, it remains unsolved. It may be that the lithium was quietly destroyed inside those ancient stars in a way we do not yet understand. It may be an error hiding in the measurements. Or it may, just possibly, be a genuine crack, a small sign of some new physics at work in the universe's first minutes. It is a useful reminder that even our most successful theories carry, somewhere in the fine print, a number that does not quite add up, and that scientists who are being honest will tell you so. The second approach to the Mako question was more direct, and it turned a prediction of Einstein's general relativity into a search tool. If the dark halo really were full of Makos, then every so often one of them should drift almost exactly between us and a distant background star. When that happened, the gravity of the Mako would bend and focus the starlight, exactly as Zwicky had imagined back in 1937, and the background star would appear to brighten smoothly and then fade over the course of days or weeks. The effect is called microlensing, and the shape of the brightening is distinctive, unlike any natural flickering of a star. Detect enough of these events, and you could weigh the total amount of Mako material in the halo. In the early 1990s, 2 large teams set out to do exactly this. Watching toward the Large Magellanic Cloud, a small companion galaxy of the Milky Way that hangs in the skies of the southern hemisphere. Because the Magellanic Cloud sits well outside our galaxy's disk, any Makos in the dark halo would lie along the line of sight to its stars. The teams monitored millions of stars, night after night, year after year, watching for the telltale brightening. They found a few events, enough to show that some Makos do exist in the halo, but the number was far too small to explain the dark matter. The Makos could account for, at most, perhaps 10 or 20% of the halo's mass. The rest was still missing, and now there was nowhere ordinary left for it to hide. By the turn of the millennium, the 2 approaches together had closed the door. The deuterium said most of the matter was not made of atoms. The microlensing said the halo was not made of dark, ordinary objects. The dark matter was not a census error, not a pile of unlit stars and planets we had simply failed to count. It was a new kind of thing, a particle that did not touch light at all, that passed through ordinary matter as if it were vacuum, whose only handshake with the visible universe was the bending of space itself. The question had changed shape. It was no longer whether such a particle existed, it was what it was, and how on earth you might ever catch one. And the most powerful single piece of evidence for all of it, the measurement that turned the dark matter from a strong inference into a precise number, comes from the oldest light there is. That light has been travelling for 13.8 billion years. It fills every direction of the sky at once. It is almost perfectly smooth, and woven into its faint imperfections is a complete recipe for what the universe is made of. The discovery of that light was an accident, one of the most famous accidents in the history of science. In 1964, 2 radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were testing an exquisitely sensitive horn antenna built for satellite communications. They kept running into a faint, persistent hiss in their data that they could not get rid of. They pointed the antenna at different parts of the sky. The hiss was everywhere, with the same intensity. They checked for interference from radio stations and from nearby radar. They found that a pair of pigeons had been roosting in the horn and coating it with droppings, so they evicted the pigeons and cleaned the antenna, suspecting the birds were the culprit. The hiss remained. It came from every direction equally, and it matched a temperature of about 3 degrees above absolute zero. What they were hearing, without yet knowing it, was the afterglow of the Big Bang. And here the history holds a quiet injustice worth remembering. 16 years earlier, the physicists Ralph Alpher and Robert Herman had predicted that exactly such a glow should exist, left over from the hot early universe, and had even estimated its temperature. Their prediction had been forgotten. A group at Princeton, led by Robert Dick, had independently realized the glow should be there and was building an instrument to look for it when they heard that 2 men at Bell Labs had already stumbled onto it by accident. Penzias and Wilson would win the Nobel Prize. Alpha and Herman, who saw it coming, would not. The cosmic microwave background is light set free at the moment the universe became transparent, about 380,000 years after the beginning. Before that, the universe was the hot, dense plasma we spoke of earlier. with electrons running free and scattering every photon, an impenetrable fog. As the universe expanded and cooled, it crossed the threshold where electrons could finally be captured by protons to form neutral hydrogen, and in that moment the fog cleared and the trapped light streamed outward in every direction. It has been travelling ever since, stretched by the expansion of space from the visible light it once was into the faint microwaves we detect today. Sit for a moment inside that early universe. Before the light broke free, there is no sky, because there is no clear space to look across. Everything is a uniform glow, a dense, brilliant fog in every direction, hotter than the surface of the sun, pressing in from all sides at once. There are no stars, because no star could exist here. There are no atoms, only a roiling soup of bare nuclei and free electrons and trapped light, all of it sloshing back and forth. And it really is sloshing. Sound waves are moving through this fog, real pressure waves, the ordinary matter falling inward under gravity and bouncing back out under the push of the trapped light, ringing through the plasma like a struck bell, while the dark matter sits quietly underneath it all, holding the wells in place and feeling none of the pressure. Then, in a single cosmic instant, the universe cools just enough. The electrons are captured into atoms, the fog clears, and the light that was trapped for all that time floods outward into a universe that has suddenly become transparent. The ringing stops, and it freezes. The pattern of those sound waves, caught at the exact moment the light was released, is what we read today in the faint hot and cold patches of the oldest light. We are, in a real sense, looking at a photograph of the last sound the universe made before it fell silent, and the dark matter's signature is written all through it. If the early universe had been perfectly uniform, this background would be perfectly featureless, and it would tell us almost nothing. But it is not perfectly uniform. Imprinted across it are tiny variations in temperature, patches very slightly hotter and very slightly colder than the average, and those patches are the seeds of everything. The slightly denser regions would go on to collapse into galaxies and clusters. The slightly emptier ones would become the voids. The precise pattern of those variations, their sizes and their strengths, and how they are distributed across the sky, depends in detail on what the universe is made of. Different ingredients leave different signatures in the light. The first spacecraft to map this glow in detail was launched by NASA in 1989 and named the Cosmic Background Explorer. It measured the temperature of the background radiation with extraordinary precision, confirming that it matched almost perfectly the glow of a body at 2.725 degrees above absolute zero, the cleanest such measurement in all of physics. It also caught the first faint hints of the temperature variations at a level of about 1 part in 100,000 and found them to be exactly the size that theories of structure formation needed them to be. The two leaders of that mission, John Mather and George Smoot, would share the Nobel Prize for the work, but the satellite could only see the largest, coarsest variations. It could not resolve the finer detail that held the real recipe of the cosmos. For that, a sharper instrument was needed. That instrument was the Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001. It mapped the microwave sky with 30 times the resolution of its predecessor, and from that map it extracted something called a power spectrum, a graph showing how much temperature variation exists at each angular scale, from broad smudges across the sky down to fine speckle. The shape of that graph is astonishingly sensitive to the contents of the universe. It rises and falls in a series of peaks. The first and largest peak fixes the total density of the universe, and its position tells us the universe is geometrically flat. The second peak, set against the first, measures the density of ordinary matter, and the fact that it is relatively low means ordinary matter is only a minor ingredient. The third peak, and the smaller ones beyond it, pin down the dark matter and refine the rest of the recipe. The pattern of those peaks is shaped by a kind of cosmic music. Before the fog lifted, sound waves rang through the plasma, ordinary matter falling into the dark matter wells and bouncing back out under the pressure of light, oscillating, while the dark matter, deaf to that pressure, simply held the wells steady. The relative heights of the odd and even peaks record that interplay, and you can read the amount of dark matter directly from them. When that probe returned its numbers, they were precise in a way the field had never seen. Ordinary matter, a few percent. Dark matter, several times more. The rest, dark energy. These were not estimates pulled from a model. They were extracted from the shape of a measured curve, with small and honest error bars. The dark matter was not merely a feature of nearby galaxies. It was written into the structure of the entire universe from its earliest transparent moment, encoded in the oldest light, legible across the whole sky. Then, in 2009, the European Space Agency launched a still more sensitive satellite named Planck, which mapped the background with a resolution and a depth that left every previous map behind. The Planck results, released in stages through the 2010s, give the values we use today as the standard. Ordinary matter, 4.9%. Dark matter, 26.8%. Dark energy, 68.3%. Set aside the dark energy and look only at the matter, and the dark portion comes to 85% of the whole. The number I gave you at the very beginning, the number that has been running quietly beneath every word since, comes from this measurement, from the faint warmth of the universe's first light. There is a final confirmation hidden in that same light, and it is worth sitting with, because it shows how tightly the whole picture holds together. The density of ordinary matter that the microwave background demands is the same density that the deuterium demands. Two completely independent methods, one reading the light from the universe at 380,000 years old, the other reading the chemistry from the universe at 3 minutes old, arrive at precisely the same answer. That is not the kind of agreement you get by accident. And there is more. The same sound waves that shaped the peaks in the microwave background also left a faint, fixed imprint on the way galaxies are spread across the sky. Galaxies are very slightly more likely to be found at a particular separation, around 500 million light-years apart, than at any other distance, a frozen echo of those primordial sound waves called the Baryon acoustic scale. It was predicted from the microwave background and then found, exactly where predicted, in vast surveys of millions of real galaxies. Rotation curves, cluster dynamics, the light elements, the failed Mako hunt, the peaks in the oldest light, the spacing of the galaxies, 6 independent windows opening from 6 different epochs and methods, and all of them showing the same thing. About 5 times more dark matter than ordinary matter, not made of atoms, untouched by light, present from the beginning, shaping all that followed and ruling the universe still. And yet every one of those windows shows us only the gravity of the dark matter. They tell us how much there is, and where it sits, and how it moves on the largest scales. Not one of them tells us what it actually is. The particle itself, the thing that makes up that trillion solar masses around the Milky Way, the thing passing through your chest as you lie there, has never been caught in any laboratory on Earth. Its mass is unknown. Its behavior, beyond gravity, is unknown. Whether it feels some hidden force of its own, whether it interacts with itself in ways we cannot see, is unknown. The most basic properties of the most common form of matter in the universe are a blank space on the map. Filling that blank has been the work of the last 40 years, and it has not gone the way anyone expected. To go looking for the particle, you first have to imagine what catching one would even feel like, from the detector's point of view. The principle is simple to state and brutally hard to achieve. If our galaxy sits inside a halo of dark matter particles, and if those particles interact with ordinary matter through some feeble force beyond gravity, then once in a great while, one of them should clip an atomic nucleus and knock it slightly, like a cue ball grazing another ball across a vast and otherwise empty table. That tiny recoil would deposit a tiny pulse of energy, perhaps a few thousand electron volts, released as a flicker of heat, or light, or electric charge. Build a detector quiet enough and sensitive enough to feel that single faint nudge, and you might, at last, register the passage of the dark matter wind. The trouble is the arithmetic of rarity. For the favoured candidate, a WIMP 100 or so times heavier than a proton, the expected event rate is staggeringly low, a mere handful of nudges per year, in a tank holding a ton of material. Meanwhile, the natural world is screaming. Radioactivity in the rock and the air and the detector itself, cosmic rays sleeting down from space, the faint decay of trace impurities in every component, all of it produces flashes at a rate millions of times higher than the signal you are hunting. Finding a dark matter event in that din is like trying to hear one whispered word from the far side of a packed stadium during the loudest moment of the show. So the first thing you do is go down, deep down. Let me put you there for a moment. You are standing in a chamber carved out of solid rock, 1.5 kilometers beneath a mountain, or at the bottom of a mine shaft that took you 20 minutes to descend in a rattling cage. The air is cool and faintly damp and smells of stone. Above your head is more rock than you can comfortably think about, and that rock is the entire point, because it is a shield. At the surface, cosmic rays pour through your body and through every instrument at a furious rate. Down here, beneath all that stone, that rain has been cut by a factor of 1 million or more. The deepest of these laboratories are some of the quietest places that exist anywhere on the planet. Not quiet in sound, but quiet in radiation, scrubbed of the constant particle storm that washes over the world above. The Gran Sasso laboratory in Italy lies beneath 1,400 meters of the Apennine Mountains, reached through a motorway tunnel. A laboratory called Snow Lab in Canada sits 2 kilometers down inside a working nickel mine. The Sanford facility in South Dakota occupies the tunnels of the old Homestake gold mine, 1,500 meters below the surface. In rooms like these, in the deep silence under the mountains, physicists wait for the dark matter to knock. Even the rock above is not enough. The detector itself has to be built from materials of almost unimaginable purity, because ordinary steel and copper and solder and circuit board all carry faint traces of natural radioactivity that would drown the signal. Every component is screened and selected for its quietness. The instruments are assembled in clean rooms by technicians in sealed suits, guarded against radon gas and dust and the faint radioactive breath of the surrounding rock, then cooled to within a hair of absolute zero, where the random jitter of heat itself falls silent and wrapped in layer upon layer of shielding. For the last 2 decades, the leading design has been the liquid xenon chamber, a great tank of ultra-pure liquid xenon, watched from above and below by hundreds of sensitive light detectors. When a particle strikes a xenon atom, it produces 2 signals, a prompt flash of light at the moment of impact, and a small cloud of liberated electrons that drift slowly upward through the liquid under an electric field, producing a second flash when they reach the top. The ratio between those 2 signals reveals what kind of particle did the striking, distinguishing the recoil of a nucleus, which is what a WIMP would produce, from the recoil of an electron, which is what ordinary background radiation produces. And because the position of the impact can be reconstructed in 3 dimensions, the experiment can ignore the noisy outer shell of xenon and watch only the pristine heart of the tank, where the background is lowest. Liquid xenon is not the only approach, and the diversity is deliberate, because a discovery believed by everyone has to be confirmed by more than one kind of instrument. Some experiments cool crystals of germanium or silicon to a fraction of a degree above absolute zero and listen for the tiny pulse of heat and the faint flicker of charge that a struck nucleus would release, reading the 2 signals together to tell a nuclear recoil from ordinary background. Others use crystals of calcium tungstate or supersaturated fluids held on the very edge of boiling, so that a single dark matter strike would trigger a microscopic bubble, like the first bubble in a glass of water about to boil. Each technology has its own strengths, its own blind spots, its own particular backgrounds to fight. If one of them ever sees a signal, the others stand ready to confirm or contradict it, using completely different physics, so that no single quirk of a single detector can be mistaken for a discovery. That redundancy is not duplication. It is the immune system of the field, the thing that lets the community eventually trust what it finds. Behind this technology stands a particular person, because it usually does. The Xenon program was founded and driven for decades by Elena April, an Italian-born physicist at Columbia University, who trained under one of the pioneers of the field, and then spent her career building ever larger and ever quieter xenon detectors at Gran Sasso. She started small, with a chamber holding a few kilograms of xenon, and over the years scaled it up through one generation after another, each larger than the last, each pushing the background lower and the sensitivity higher. The detectors grew from a few kilograms to tens of kilograms to a full ton and beyond. This is the rhythm of the whole field. A physicist commits a working lifetime to a single quarry, builds a machine of extraordinary delicacy, and waits. The current leader is an experiment called LUX Zeppelin, in the South Dakota mine, which holds 7 tons of active liquid xenon and began taking data in 2022. It is the most sensitive instrument of its kind ever built. There is a strange and humbling limit waiting at the end of this road, and the most sensitive detectors are now beginning to draw close to it. The same xenon tanks that hunt for dark matter are also, unavoidably, sensitive to neutrinos, the flood of ghostly particles pouring out of the sun, raining down from the upper atmosphere, and drifting in from ancient exploded stars. Neutrinos interact almost as feebly as dark matter is expected to, and as the detectors grow ever larger and ever quieter, they will eventually begin to register the gentle nudges of these solar and cosmic neutrinos, nudges that look maddeningly similar to the signal of a passing dark matter particle. This approaching wall of unavoidable neutrino events has been given a name that carries its own quiet dread: the neutrino fog. Beyond a certain sensitivity, telling a real dark matter signal apart from the steady background of neutrinos becomes extraordinarily difficult, because the two can look almost the same. The hunt has perhaps another generation of detectors before it reaches that fog. If the particle has not been found by then, the search will not be over, but it will become a very different and much harder kind of search, one that has to see through a haze that cannot be removed. And the result of all of it, across decades of work and several generations of detectors, can be stated in a single sentence: they have seen nothing. No WIMP. No dark matter recoil rising above the expected background. This is not a failure of the machines. The machines have performed exactly as designed. What they've done is rule out, one region at a time, the places where the WIMP was supposed to live. On the graphs that physicists use to track the hunt, the boundary of the excluded territory has marched steadily downward, year after year, sinking below the very thresholds where the most elegant theories predicted the particle ought to be. The WIMP was supposed to be a near certainty. There was a beautiful coincidence, known as the WIMP miracle, in which a particle with roughly the mass and the feeble interactions expected from a certain extension of particle physics would, all on its own, be produced in the early universe in exactly the abundance needed to be the dark matter. It was the kind of coincidence that feels like a clue. To see why it gripped the field so hard, you have to understand where the candidate came from. Particle physicists had, quite independently of any dark matter problem, proposed a theory called supersymmetry, an elegant extension of the known laws that would solve several deep puzzles in their own field, and that predicted, as a byproduct, a whole new family of heavy particles. The lightest of those new particles would be stable, and it would interact only weakly. And when physicists calculated how much of it would survive from the hot early universe, the number that fell out was, astonishingly, just about the amount of dark matter the cosmos appears to contain. Two completely separate lines of reasoning, one from particle physics trying to tidy its own equations, one from astronomy weighing the galaxies, seemed to be pointing at the very same object. That convergence was intoxicating. It promised that a single discovery might solve two great problems at once: the missing matter of the universe and the missing pieces of particle theory, in one stroke. For 30 years it guided the entire field, and the longer the detectors stay silent, the more that miracle looks less like a clue and more like a coincidence that quietly led us astray. There has been one stubborn exception, and it has become one of the longest-running arguments in physics. An experiment at Gran Sasso, called DAMA, and later expanded under the name DAMA Libra, has been running since 1995. Instead of liquid xenon, it uses crystals of sodium iodide, and for more than 20 years it has reported a signal that no one can quite explain away or confirm. The signal is an annual rhythm. The rate of events in the crystals rises and falls over the course of each year, with a regular cycle peaking in early June and bottoming out in December. This is, remarkably, exactly what a dark matter wind should produce. As the Earth orbits the Sun, its velocity through the surrounding halo of dark matter changes. In June, the Earth's motion around the Sun adds to the Sun's own motion through the galaxy, so we plough through the dark matter faster and feel a stronger wind. In December, the two motions partly cancel and the wind softens. A stronger wind means more particles and more energetic nudges, and so a higher count in the crystals. The idea that the dark matter signal should breathe with the seasons in just this way was worked out by theorists in the 1980s, and the experiment's annual rhythm matches the prediction with uncanny fidelity. The deeper beauty of this strategy is that it offers a way to pull a dark matter signal out of a sea of noise, even when you cannot point to any single event and call it special. Most of the background that plagues these experiments does not care what month it is. Radioactivity ticks along at the same average rate in June as in December, but the dark matter wind does change with the season, in a very particular way, peaking on a date fixed by the geometry of the Earth's orbit, and swelling and fading by a precise, predictable amount. So even if no individual flash can be told from the background, a signal that rises and falls on exactly that astronomical schedule, cresting in early June, is extraordinarily hard to counterfeit with any ordinary earthly process that happens to keep a yearly cycle. That was the elegance of the approach, and it is a large part of why the claim has been so stubbornly difficult to dismiss outright. The signal is also extremely strong in statistical terms. The team behind it claims a confidence so high that the odds of it being a random fluctuation are, for all practical purposes, nil. Something real is making those crystals tick with the calendar. The problem is that no other experiment has ever seen anything like it. The xenon detectors, the germanium detectors, the silicon detectors, all of them stare at the same patch of theoretical territory and see only silence. If the annual rhythm were caused by WIMPs scattering off the sodium and iodine in the crystals, then the xenon experiments, which are far more sensitive, should have logged hundreds or thousands of events by now. They have logged none, so the field is left with a genuine puzzle. Theorists have proposed that perhaps the particle interacts in some special way that favours sodium and iodine over xenon, or that the rhythm is caused by something entirely mundane, a seasonal swing in some background, a flux of radon gas, a temperature cycle in the electronics, anything that keeps time with the year. The team insists their signal is robust and has answered every objection. The wider community remains unconvinced. The only clean way to settle it is for another experiment to use the very same sodium iodide crystals and see whether the rhythm reappears. Several are now trying, one in South Korea and one in Spain among them, and so far they have not reproduced it, though the data are not yet decisive. The whole saga is a hard reminder of how treacherous this search is. Even the most careful experiment in the world can be fooled by a background no one thought to consider. There was another flutter of excitement in 2020. One of the large xenon experiments reported a small excess of low-energy events, around 53 more than the expected background of 232. It was statistically interesting, and the physics community lit up. Within days, papers were appearing online exploring what it might mean, whether it could be a sign of Axions streaming out of the sun, or some new interaction in a hidden sector of physics. But the team itself was careful and refused to claim a discovery, laying out the possibilities and leaving the question open, and they flagged a far more boring candidate explanation. Tritium. Tritium is a radioactive form of hydrogen, and a few atoms of it per kilogram of xenon, a contamination so faint it could never be measured directly, would produce exactly the kind of low-energy events seen in the excess. When more data came in from the next, upgraded version of the detector, the excess melted away. Tritium, almost certainly, all along, the moment passed, and the deep silence returned. The hunt has never been confined to the WIMP. There is a second great candidate, and in recent years it has been gaining ground precisely because the WIMP has stayed silent. It is the Axion, a particle first dreamed up in the 1970s to solve an unrelated problem in the theory of the strong nuclear force, and only later realized to be a beautiful candidate for dark matter as well. The problem it was invented to solve is a subtle one. The equations of the strong force, the force that binds quarks into protons and neutrons, contain a term that, as far as anyone can tell, ought to make neutrons behave in a particular lopsided way, giving them a slight electrical asymmetry. Experiments have searched for that asymmetry with enormous precision, and found it to be, as near as can be measured, exactly zero. The term that should produce it appears to be switched off, finely tuned to nothing, for no reason anyone could explain. Two physicists proposed an elegant fix, a new symmetry that would naturally drive that term to zero, and a third pointed out that the fix implied the existence of a new particle, fantastically light and almost perfectly invisible. It was named the Axion, after a brand of laundry detergent, because it cleaned up the problem. Only later did physicists notice that a particle with exactly those properties, produced in the right way in the early universe, would also be a near-perfect dark matter candidate. One idea, born to tidy up a wrinkle in nuclear theory, turned out to possibly solve the largest missing matter problem in the cosmos. The Axion would be fantastically light, billions of times lighter than the WIMP, so light that it would behave not like a hail of separate bullets, but like a vast, coherent, gently oscillating field filling all of space. Catching it requires a completely different kind of trap. One leading experiment, at the University of Washington, places a finely tuned microwave cavity inside a powerful magnetic field, on the principle that an axion passing through can, very rarely, convert into a single faint photon, a whisper of microwave light at a frequency set by the axion's mass. The experiment scans slowly across a range of frequencies, listening for a faint pure tone to rise out of the noise, like someone turning a radio dial with infinite patience, searching for one station that may or may not be broadcasting. It has not heard the tone yet, but it has ruled out broad stretches of the dial, and a whole family of other axion searches, using other clever tricks, is now sweeping the rest. And there is a third front, at the opposite extreme of energy. Rather than wait for dark matter to drift in from space, you can try to manufacture it. The Great Particle Collider at CERN, on the border of France and Switzerland, smashes protons together at very nearly the speed of light, and if dark matter particles couple to ordinary matter through the right forces, some of those collisions should produce them. They would leave no direct trace, but they would carry energy away with them as they fled the detector, showing up as a telltale imbalance, a chunk of missing momentum where something invisible escaped. The collider has searched long and hard for that signature, and for the supersymmetric particles whose theory underwrote the WIMP in the first place. It has found neither. The absence of those particles at the collider, set beside the silence in the deep detectors and the quiet in the axion cavities, has closed off the simplest and most cherished versions of the WIMP story. There is a third way to hunt for the dark matter, beyond building it in a collider and waiting for it underground, and it turns the whole problem inside out. Several of the leading candidate particles would be their own antiparticles. If that is true, then wherever the dark matter is densest, particles should occasionally collide and annihilate one another, converting their mass into a burst of ordinary radiation, a flash of gamma rays, or a spray of ordinary particles that fly off into space. We cannot see the dark matter itself, but we might just be able to see the light of its own self-destruction. This is called indirect detection, and instead of sending physicists underground, it sends them to the places in the sky where the dark matter is expected to pile up most thickly, to ask whether anything unexpected is glowing there. The most natural place to look is the center of our own galaxy, where the dark halo is denser than anywhere else within reach. And there is, in fact, an excess of gamma rays coming from the galactic center, a faint glow that a space telescope called Fermi has mapped patiently over more than a decade, a glow somewhat brighter than the known sources can easily account for. For a while, this galactic center excess was one of the most tantalizing hints in the entire field. Its shape and its spectrum matched, suggestively, what annihilating dark matter might be expected to produce. But the center of the galaxy is a crowded and violent place, thick with the corpses of stars, tangled with magnetic fields, swarming with exotic objects. And the more carefully astronomers studied the glow, the more it began to look as though it could be produced by a large hidden population of rapidly spinning neutron stars, each too faint to pick out on its own, but together able to mimic the signal. The hint has not been confirmed. It has not been ruled out. It sits, like so much in this subject, in the uncomfortable middle ground of perhaps. So astronomers looked for cleaner targets, and the cleanest of all are those tiny dwarf companions of the Milky Way, the ones that are almost pure dark matter. They hold almost no gas and almost no ongoing star formation, almost none of the messy astrophysics that confuses the galactic center, and yet they are dense with the dark stuff. If dark matter annihilates, these little galaxies ought to shine faintly in gamma rays, and because they are so quiet in every other way, even the faintest glow would stand out against the dark. The Fermi telescope has stared at dozens of them, year after year. They remain dark. No glow has appeared, and that silence, like the silence under the mountains, has been turned into a limit, ruling out yet another stretch of the possibilities. There have been other hints from other directions. An unexplained excess of antimatter positrons in the cosmic rays measured by an instrument bolted to the side of the space station. A possible faint line in the X-rays from distant clusters of galaxies. Each, on closer inspection, has either faded or found a more ordinary explanation. The dark matter, if it destroys itself at all, does so far too rarely for us to have caught the light of it yet. There is one indirect hint that refuses to fully die, and it is worth a moment because it points at a different candidate entirely. In 2014, two separate teams, studying the X-rays from clusters of galaxies and from the Andromeda galaxy, reported a faint, unexplained spectral line, an excess of X-rays at one particular energy that matched no known atomic transition. One natural explanation was a sterile neutrino, a hypothetical heavier cousin of the ordinary neutrino, slowly decaying and producing exactly such a line. A sterile neutrino would be a beautiful dark matter candidate, lying somewhere between the cold WIMP and the cold axion in its properties. But the line was extraordinarily faint, right at the edge of what the instruments could measure, and other groups looking at other objects failed to find it where it should have been. Like the galactic center glow, it has neither been confirmed nor entirely dismissed. A new generation of X-ray telescopes may finally settle whether that faint line was the decay of dark matter or simply a trick of imperfect instruments. So the field has shifted, and the mood has shifted with it. The WIMP miracle, which steered a whole generation of physicists, now looks less like a prophecy and more like an assumption that happened to land on a pleasing number. The community has widened its gaze. Axions, sterile neutrinos, primordial black holes, dark photons, asymmetric dark matter, entire hidden sectors of physics, with their own forces and their own families of particles, all of these are now being pursued with new experiments and new ideas. The search is broader and stranger than it was 20 years ago, and far more open to the possibility that the answer will come from a direction nobody is currently watching. One of those candidates deserves a moment of its own, because it is the single idea that would require no new particle at all. Perhaps the dark matter is black holes. Not the kind made from dying stars, but primordial black holes formed in the first instance of the universe. In places where the density was so high that matter collapsed directly into black holes before a single star had ever shone, they would be perfectly dark. They would interact only through gravity, and they would be made of nothing exotic, nothing beyond the physics we already know. The idea is old, and it had largely faded into the background, until the detection of gravitational waves from merging black holes brought it roaring back, because some of the black holes those detectors found turned out to be heavier than the simplest models of stellar death comfortably allow. Could some of them be primordial, survivors from the dawn of time? Could the dark matter be a vast, unseen population of black holes drifting between the stars? For most ranges of mass, the answer now appears to be no. If there were enough black holes of a given size to make up the dark matter, they would give themselves away by the microlensing of background stars as they drifted across them, or by disturbing the delicate structures of the early universe. And across most of the possible masses, those searches have come up empty. A few narrow windows remain stubbornly open. It is probably not the answer, but it stands as a reminder that even the assumption of a new particle is, in the end, only an assumption. After 4 decades of looking, the dark matter particle is as elusive as it was on the day the search began. The detectors have grown more sensitive by enormous factors. The backgrounds have been beaten down to levels the pioneers would have called impossible. And still, nothing. No nucleus has been nudged in a xenon tank. No tone has risen in a microwave cavity. No missing energy has appeared at the collider. The particle that makes up 85% of all matter has simply refused to show its face. That long silence carries a real weight, and it has pressed hard on the people who chose to spend their lives inside it. Some of them have given 30 years to building and tending detectors that have caught nothing at all. The field has had to learn a difficult discipline, the discipline of the null result, the patient work of drawing one more boundary, excluding one more possibility, and moving on without the reward of discovery. It is not the kind of science that wins prizes or makes headlines. Most of the time, it is slow, methodical, and incremental, and it asks of its practitioners a tolerance for not knowing that is rare even among scientists. But the silence is not empty. Every null result is itself a measurement. Every excluded region is a step toward the truth, even if the truth turns out to be that we have been asking the wrong question all along. It is worth pausing to think about what a single confirmed detection would actually mean, because the stakes are larger than one entry in a textbook. If, some night, in a tank of xenon beneath a mountain, a nucleus were nudged in just the right way, with just the right signature, and another detector somewhere else confirmed it, we would, for the first time in history, hold a piece of the universe's dominant substance. We would learn its mass, the first hard number about the particle itself in nearly a century of knowing it was there. We would learn whether it feels forces beyond gravity, and that would open a door onto whatever hidden physics lies beneath the world we know, physics that the Great Collider has been unable to reach. It would tell us that the standard model of particle physics, the catalogue of everything we are made of, is not the whole story, that there is a second sector of reality woven through our own, mostly silent, occasionally whispering. The discovery would not change your daily life by a single degree. The particles would keep passing through you exactly as before, but it would change what we are, in the deepest sense, because it would mean that for the first time we understood the stuff that built the house we live in, the scaffolding that made the stars and therefore made us. That is what the people under the mountains are waiting for. Not fame, most of them, and not even certainty. Just one clean knock from the dark to prove that the thing we have been tracking by its shadow for 90 years is finally, undeniably, here in our hands. The absence of the WIMP, in the detectors and at the collider, has forced the field to reconsider assumptions that felt like bedrock 20 years ago. The particle that seemed all but guaranteed may simply not exist. The answer may be stranger, or simpler, or hiding in a corner of the possibilities that is much harder to reach. And there is one more option, one that a small band of physicists has been pressing for decades, growing a little less lonely each year the detectors stay quiet. The reason we cannot find the dark matter particle, they argue, is that there is no dark matter particle. The whole vast edifice, they say, rests on a misunderstanding of gravity itself. The man at the centre of that argument did not set out to be a heretic. Mordechai Milgrom was a physicist at the Weizmann Institute in Israel, and in the early 1980s, on a long sabbatical at the Institute for Advanced Study in Princeton, he was turning over the same rotation curves that everyone else was puzzling about. The standard reading was already settling into place. Stars at the edges of galaxies move too fast, therefore each galaxy must be wrapped in a dark halo, supplying the extra gravity. Milgrom looked at the numbers and asked a different question. What if the problem was not the mass, but the law? What if gravity itself behaved differently than we assumed? Out there in the faint outer reaches of a galaxy, he noticed something that others had passed over. The discrepancy between the visible mass and the observed speeds did not appear just anywhere. It switched on at a particular threshold, a particular value of gravitational acceleration. Where the pull of gravity was strong, in the bright inner regions of galaxies and everywhere in the solar system, the old laws of Newton held perfectly. But below a certain critical acceleration, a pull so gentle it is roughly 100 billion times weaker than the gravity you feel standing on the Earth, the predictions began to fail and the rotation curves went flat. And the threshold seemed to be the same everywhere. Galaxy after galaxy showed the same pattern, and the transition always came at about the same faint acceleration. So Milgrom proposed a single, bold modification. Instead of adding invisible matter, change the relationship between gravity and acceleration once the pull drops below that threshold. With that one change, governed by a single new constant of nature, he could take the visible matter of a galaxy, the stars and gas you can actually see, and predict its rotation curve, with no dark halo at all. The predictions were uncannily good, galaxy after galaxy. The observed curve fell almost exactly where his formula said it would. He published the theory in 1983 and called it modified Newtonian dynamics, which everyone shortened to MOND. The paper was not so much rejected as quietly declined. The dark matter picture was already hardening into orthodoxy, and most astronomers saw no reason to throw out Newton's gravity when an invisible halo solved the same problem and fit so neatly with everything else. But Milgrom was not the first to think of modifying gravity, and where the earlier attempts had been clumsy, adjusting the force law galaxy by galaxy with no guiding principle, his had a single elegant idea at its core, One number, one critical acceleration that worked across the whole family of galaxies, from the faintest dwarfs to the grandest spirals. In his scheme, a galaxy's rotation curve was not a free shape you tuned by hand. It was a prediction derived from the visible matter alone, and the prediction worked. It still works, at the scale of individual galaxies, and that is what keeps the idea alive against very long odds. Again and again, when a new galaxy's rotation is measured, the modified gravity formula fits it. When the visible matter is lumpy and irregular, with bumps and dips in its distribution, the formula predicts matching bumps and dips in the rotation curve, and those wiggles are often exactly what observers find. The standard dark matter picture struggles with this. Why should the invisible halo, which is supposed to dominate the mass, arrange itself so precisely as to mimic the pull of the visible matter, feature for feature? In recent years, this puzzle has been sharpened by an astronomer named Stacy McGaugh and his collaborators, who showed that across a huge range of galaxies, there is a remarkably tight relationship between the gravity you observe and the gravity you would predict from the visible matter alone. That tight relation is exactly what the modified gravity idea predicts as a law of nature, and it is something the dark matter picture has to work hard and add fine detail to reproduce. There is even a strange numerical coincidence that some find suggestive. Milgrom's critical acceleration, the threshold where everything changes, turns out to be close to a fundamental cosmic acceleration you can build from the size and expansion of the universe itself, as if the behavior of gravity at the edge of a single galaxy somehow knows about the universe as a whole. No one knows whether that coincidence means anything, but it is the kind of thing that keeps honest people awake. The trouble is that the modified gravity idea, for all its successes inside galaxies, runs into severe problems the moment it leaves them. The original theory was not relativistic. It was a modification of Newton's laws, and you cannot build a universe out of Newton's laws alone. You cannot describe the bending of light, or the expansion of the cosmos, or the behavior of the oldest light, without a theory consistent with Einstein's general relativity, which has passed every precision test ever thrown at it. In the solar system, in binary pulsars, in the detection of gravitational waves from colliding black holes. Relativistic versions of the modified gravity idea were eventually constructed, but they were mathematically baroque, and they had to introduce new fields and new parameters that sacrificed the original, beautiful simplicity, and then they had to face the two pieces of evidence that the idea handles worst of all. The first is the collision we have not yet looked at directly, and it is the single cleanest test ever devised to tell dark matter and modified gravity apart. It is a pair of galaxy clusters, 3.7 billion light-years away, caught in the middle of a catastrophic collision, and it is known as the Bullet Cluster. Around 150 million years before the light we now see set out, a smaller cluster tore straight through a larger one at a speed of roughly 4,700 kilometers per second, one of the most violent events the universe has produced since the Big Bang. To understand why this collision is so revealing, you have to know that a cluster of galaxies is made of three quite different things. Picture it slowed down, the way no human eye could ever actually watch it, across 150 million years compressed into a moment. Two great cities of galaxies drift toward each other through the dark, each one a swarm of hundreds of bright spirals and ellipticals, each one wrapped in an invisible halo and filled with a glowing sea of hot gas. They meet, and in the meeting, the three things they are made of come apart, because each one responds to the collision in its own way. First, the galaxies themselves, which are mostly empty space, so far apart that even in a head-on collision between clusters they almost never strike one another. They sail through largely untouched, their paths bent only by gravity. Second, the hot gas that fills the space between the galaxies, which actually holds most of the ordinary matter in a cluster, far more than the galaxies do. When two clusters collide, this gas does not pass through cleanly. It slams together and drags, like two crowds running into each other, heating to hundreds of millions of degrees and slowing down, falling behind. And third, the dark matter. If the dark matter is a collisionless particle, it should behave like the galaxies, not like the gas. It should sail straight through the collision and stay with the galaxies, while the gas is stripped away and left behind in the middle. That is exactly what we see. The hot gas, glowing in X-rays, was mapped by the Chandra X-ray Observatory, and it sits in the middle of the wreck, trailing behind in two great shock fronts, shaped like the bow waves of ships. The galaxies, mapped in ordinary light, sit ahead of the gas, two clean groups that have already passed through and kept going. And then there is the total mass, which can be weighed without seeing it at all, through gravitational lensing, the very effect Zwicky imagined in 1937. The mass of the cluster bends the light of more distant galaxies behind it, distorting their images into faint arcs, and by measuring those distortions, astronomers can map where the mass actually lies, whether it shines or not. A team led by Douglas Clow made that map, and the answer was unambiguous. The mass was not with the gas. The mass was with the galaxies. Two concentrations of unseen mass, sitting squarely on the two groups of galaxies, cleanly separated from the hot gas stranded in the middle. If there were no dark matter, and gravity simply followed the ordinary matter, then the mass should track the gas, because the gas is where most of the ordinary matter is. It does not. The mass tracks the galaxies, exactly as a collisionless dark matter particle demands. The image of the bullet cluster, with its two pools of unseen mass glowing apart from the stranded gas, became the defining picture of the whole subject. The photograph that seemed to say, "Here it is, point to it," the dark matter, caught in the act of passing through. The bullet cluster is not the only collision of its kind, though it remains the cleanest. Astronomers have since found others, including an enormous and gloriously named system far across the universe called El Gordo, the Fat One, a pair of massive clusters smashing together with the same telltale separation of mass from gas. There was one apparent exception that caused a stir for a time, a system nicknamed the Train Wreck, where the earliest maps seemed to show a clump of dark matter sitting all alone, with no galaxies attached to it, a result that would have been very hard to explain and might have undermined the whole picture. But sharper observations with better lensing data eventually dissolved the anomaly, bringing it back into line with everything else. One collision after another tells the same story. The mass travels with the galaxies, the gas is left stranded behind. The pattern is the same wherever we look. These collisions do more than confirm that dark matter exists. They also tell us something about how the dark matter behaves toward itself, which is one of the few handles we have on its hidden nature. If the dark matter particles felt some force of their own, a dark force we cannot see, then in a collision as violent as the bullet cluster, the two dark halos should have dragged against each other, slowed, and fallen behind the galaxies, at least a little. They did not. The dark matter sailed through almost untouched, which means that whatever the particle is, it barely interacts even with other dark matter. The collisions of clusters have been used to place a limit on this self-interaction, and the limit is strict. The dark matter is very nearly frictionless, even against itself. A small amount of self-interaction is still allowed, and some physicists actively hope for it, because a gently self-interacting dark matter might smooth out the sharp central cusps that the simulations predict and the dwarf galaxies seem to lack. But a strongly interacting dark matter is ruled out. Whatever fills these clusters slips through everything, including itself, almost perfectly. Defenders of modified gravity have argued that it can still be accommodated if one adds a large amount of mass in ordinary neutrinos, but the neutrino masses required are larger than the rest of physics allows, and the fix feels strained. Most cosmologists regard the bullet cluster as the collision that broke the modified gravity idea. The second problem is the oldest light again, the peaks in the microwave background. That delicate pattern of peaks is a natural prediction of a universe filled with cold dark matter, and the modified gravity theories have struggled badly to reproduce it. They can manage the first peak, but the second and third, the very peaks that encode the ratio of dark matter to ordinary matter, do not come out right unless you add something that behaves, for all the world, like dark matter. The precise measurements from Planck have only made the difficulty sharper. Milgrom has never conceded. He goes on publishing, refining, pointing to the places where the dark matter picture struggles and his own succeeds, and the small community of modified gravity physicists goes on developing new theories and testing them against new data. They are not cranks. They are serious scientists holding a minority position and defending it with mathematics and evidence. And the history of science is full of minority positions that turned out to be right, and just as full of ones that turned out to be wrong. The modified gravity idea is probably wrong. But the fact that it has not been entirely killed, that it still fits some data better than the standard picture does, is a useful irritant. It keeps the dark matter community honest. It keeps reminding everyone that all the evidence for dark matter is gravitational, and that the gravitational evidence rests on the assumption that Einstein's gravity holds true on every scale, from the laboratory to the largest structures in the cosmos. That assumption is superbly well supported, but it is still an assumption. Even inside the standard picture, where dark matter is taken as real, there are unsolved problems, and the most stubborn of them live at the smallest scales. Vast computer simulations of cold dark matter, run for months on the largest machines available, make detailed predictions about how the dark matter should be arranged in and around individual galaxies. Those predictions do not match the observations cleanly. The first mismatch is called the cusp core problem. The simulations predict that the density of dark matter should spike sharply toward a galaxy's center, forming a steep cusp, but the observed motions of stars and gas in many small galaxies suggest the density there is gentler, flatter, more like a smooth core. The second is the missing satellites problem. The simulations predict that a galaxy like the Milky Way should be surrounded by hundreds or even thousands of small clumps of dark matter, each one capable of hosting a little dwarf galaxy. For a long time, we knew of only a few dozen such satellites around the Milky Way, far short of the prediction. The third is called, with the field's usual flat humour, too big to fail. The largest predicted satellite clumps are so massive that they should certainly have held on to their gas and lit up with stars, and yet the brightest dwarf galaxies we actually see are less dense than those simulated giants, as if the most massive predicted satellites somehow failed to shine when they had no business failing. These problems may be real cracks in the theory, or they may be artifacts of the parts of the physics we model worst. Simulating a galaxy is staggeringly hard. You have to model not just the smooth pull of dark matter, but the messy, violent behavior of ordinary matter, gas cooling and heating, stars forming and then detonating as supernovae, black holes blasting energy outward, magnetic fields threading through everything. When stars form and explode, they dump enormous energy into the surrounding gas, and that energy can shove gas out of the center of a small galaxy, softening a sharp cusp into a gentle core. It can heat the gas in the smallest clumps and stop them ever forming stars, which would hide the missing satellites as dark, empty halos. It can disturb the largest clumps enough to address the too big to fail puzzle. The latest simulations, which include these violent feedback processes in far more realistic detail, do appear to bring the predictions much closer to what we see. And on the observational side, the missing satellites are slowly turning up. Enormous sky surveys have been discovering faint dwarf galaxies around the Milky Way that were simply too dim to find before, steadily filling in the gap between prediction and count. There is one more small-scale puzzle that has proven harder to wave away, and it cuts a little closer to the bone. It is called the diversity of rotation curves. When astronomers survey many dwarf and low-brightness galaxies of similar total mass, they find a surprising variety in how the dark matter inside them is arranged. Some show steeply rising rotation curves, pointing to dense, concentrated dark cores. Others, of apparently the same mass, show gently rising curves, pointing to spread out, low-density cores. The standard cold dark matter picture predicts that galaxies of similar mass ought to look broadly alike in this respect, and the sheer spread of what we actually observe is not easy to reproduce. It is exactly the kind of detailed, awkward fact that the modified gravity camp likes to point to, because their formula, working from the visible matter alone, naturally produces a tight relationship that some find easier to square with the data. Whether that diversity is a real failure of the dark matter picture, or simply a sign of how violently and unpredictably real galaxies are reshaped by their own exploding stars, is one of the genuinely live arguments at the frontier right now. The debate is not settled, but even if every one of these small-scale puzzles is resolved by better modelling, they leave behind an important caution. The dark matter picture works superbly on the largest scales, the scales of clusters and filaments and the oldest light. On the smallest scales, where the dark and the ordinary are tangled tightly together, it demands care and humility and a great deal of difficult physics. The boundary between the dark and the bright is not as clean as the particles' indifference to one another might suggest. So where does that leave us after a century of work? From Zwicky weighing the Coma cluster to Rubin watching Andromeda spin, from the oldest light to the bullet cluster, from the deepest detectors under the mountains to the Great Collider on the French border, we know more about dark matter than we have ever known, and we still cannot tell you what it is. We know where it is. We know how much there is. We know it is not made of protons and neutrons. We know it is cold and slow and all but collisionless on the scales we can watch. We know it went first, that it built the scaffolding of the universe, and that without it there would be no galaxies, no stars, no planets, and no one anywhere to wonder about any of it. But we do not know its name. We have never held it. It pours through us and leaves no mark. The search goes on. New detectors are being built, deeper and quieter than any before them. The next generation of xenon experiments is already being designed to hold not 7 tons, but many tens of tons of liquid, pushing the sensitivity down toward that looming wall of neutrino fog, determined to search every last accessible corner where the particle might still be hiding. New Axion experiments are sweeping ever wider ranges of frequency, listening for that faint, pure tone. New telescopes are being trained on the dwarf galaxies and the deep sky, hunting for the glow of annihilation and mapping the dark web in ever finer detail. New theories are being written, reaching past the WIMP and the Axion into hidden sectors with their own forces, into the strange possibility that the dark matter is not one substance at all but a whole dark ecology, as varied and intricate as the visible world we know. The next generation of experiments may finally catch it. They may not. The silence may go on deepening, and if it does, that too will be a result. A sign that the truth lies somewhere we have not yet learned to look. The room is dark again. You have been listening for a while now, and the particles I described at the very beginning are still passing through you. They have been passing through you this whole time. Through the walls, through the floor, through the chair and the air and the quiet space inside your chest. They have not stopped. They will not stop. They were here before the Earth formed, before the sun first caught light, before the galaxy itself had gathered into its slow spiral, and they will still be here long after everything we have ever built has crumbled back into dust. The number I gave you at the start is the number I want to leave with you now. About 85% of all the matter in the universe is this kind of matter. Everything you have ever seen, every star, every planet, every living thing, every mountain and ocean and drifting cloud, every person you have ever loved, every work of art and every act of kindness, every moment of beauty that has ever existed anywhere, all of it is made from the minor ingredient, the 15%. The universe is mostly something else, something invisible, something that does not share our substance, something that built the stage on which we briefly appear and play out everything that matters to us, and then pass on. I have told you the story of how we came to know this. It began with a difficult man in California who weighed a swarm of galaxies and found it impossibly heavy, and who, in the same handful of years, foresaw neutron stars and gravitational lensing decades before anyone could confirm them. It went on through a careful woman at a telescope who watched the stars of Andromeda move too fast and trusted her data when the field around her did not. It passed through the oldest light in the universe, which carries in its faint warmth a complete accounting of what the cosmos is made of. It reached a moment of clarity in a pair of colliding clusters where the dark matter was caught separated from the gas, weighed by the bending of light, revealed at last as a substance you could point to, and it has brought us here, to the present, where instruments wait in the deepest quiet we can build, listening for a single particle to stir, and hearing nothing at all. Fritz Zwicky died in 1974, long before his dark matter was taken seriously, remembered as a difficult genius who was right about more things than anyone of his time believed, and who never got the recognition he was sure he was owed. Vera Rubin died in 2016, at the age of 88, having lived long enough to watch her flat rotation curves turn into one of the central questions of physics. She never claimed to know what the dark matter was. She only said that she hoped someone, someday, would work it out, and that the universe had always turned out stranger than anyone imagined, and that the wise thing was to be ready to be surprised. The search she helped to begin is now in its 5th decade. It has cost billions and employed thousands, and it has produced, so far, no particle. And yet, it is not a failure. It is the long, slow, patient labour of asking a question that genuinely matters, and refusing to pretend you have the answer before you do. The dark matter is here, in this room, in your body, in the spaces between the stars. That it exists is beyond doubt. What it is remains a blank on the map, a blank we have been filling in slowly, from the edges, with the negative outlines of everything it is not. Knowing what something is not is a real kind of knowledge. It is the necessary preparation for the moment, if that moment ever comes, when someone watches a signal climb out of the noise at last, and the name of the invisible is finally spoken. Until then, the particles go on. They pass through you as though you were not there. They do not touch you. They ask nothing of you. They are the silent majority, the dark architecture, the thing that went first and made everything else possible. You exist because they exist. You will never feel them. They are in the room with you right now, and they are not going anywhere, and we do not know what they are. We know where. We do not know what. Good night.